In this session, I am going to discuss about combination of capacitors. Capacitors can be connected in series combination, or it can also be connected in parallel combination. Fine. Now let us discuss about the series combination of capacitors. Look at this slide here. 3 capacitors of capacitances C1, C2 and C3. And these 3 capacitors are connected in series. Series combination means end-to-end connection. Okay. The negatively plate of the first capacitor is connected to the positively charged plate of the second capacitor. So in this way, the capacitors are connected. Fine. The entire combination is connected to a source of electricity whose potential difference is V. Now, what is the net capacitance of this combination? Fine. When capacitors are connected in series, potential difference across each capacitor is different, whereas the charge acquired by each capacitor is same. As per the principle of capacitor, the charge acquired by each capacitor will be same when 3 or more than 3 capacitors are connected in series. Fine. Look here, 3 capacitors are connected in series, and in turn they are connected to a source of electricity whose potential difference is V. Fine. As I have told you that across each capacitor, potential difference is different. V1, V2, V3. So, the net potential difference V is equal to V1 plus V2 plus V3. Fine. As we know that C is equal to Q upon V, or V is equal to Q upon C. So by using this, we can write that V1 is equal to Q by C1, V2 is equal to Q by C2, and V3 is equal to Q by C3. Q is same because charge acquired by each capacitor is same. Then, if you substitute all these equations, that is V is equal to Q by C, V1 equal to Q by C1, V2 equal to Q by C2, V3 equal to Q by C3, in this equation, you call this is equation number 1 and call this is equation number 2. Substitute 2 in 1, we get V is equal to Q by C, you put here, so we get Q upon C is equal to Q upon C1 plus Q upon C2 plus Q upon C3. Q you take common and cancel it. So what you get is 1 upon C equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3. Fine. Here we can choose some values of capacitances of capacitor. Suppose if C1 is 2 microfarad, C3 is 3 microfarad and C2 is 3 microfarad, C3 is some 5 microfarad. Then what will be the net capacitance? Choose C1 equal to 2 microfarad, C2 equal to 3 microfarad and C3 equal to 5 microfarad. So what will be the net capacitance? 1 upon C is equal to 1 upon 2 plus 1 upon 3 plus 1 upon 5. And this will be 5 3s are 15, 15 2s are 30, so LCM is 30. 2 15s are 3, 2 15s are 3 5s are 2 15s are 30, 3 10s are 30 plus 5 6 are 5 6 are. So what you get is 1 upon C equal to 30, then this 15 plus 10 is 25, 25 plus 6 is 31. Therefore, you get C1 equal to 30 by 31 microfarad. Sorry, C equal to 30 by 31 microfarad. So like this, we can choose any number of capacitors of different capacitance, and we can get the net capacitance. Here, reciprocal of net capacitance is equal to sum of the reciprocals of the individual capacitances. Okay. Now we will look into the second derivation, that is combination of capacitors in parallel. Parallel combination of capacitors. When 3 or more capacitors connected in parallel combination, C1, C2, C3, all of them are connected in parallel, and they are also connected to a source of electricity, that's battery, of potential difference V. Fine. Its capacitance is C1, C2, C3, and the direction of current is shown from positive terminal to negative terminal. Fine. In parallel combination, potential difference across the capacitor is same, but charge acquired by the capacitor is different. So, the net charge acquired by the capacitor is Q is equal to Q1 plus Q2 plus Q3, the net charge. Then, by the definition of capacitance, C is equal to Q by V, and then Q is equal to CV, Q1 is equal to C1V, and Q2 is equal to C2V, Q3 is equal to C3V. Call this is equation number 2, and then call this equation number 1. Substitute 2 in 1. We get Q is CV. Here, charge acquired by each capacitor is same. Q. This side plus Q, this side minus Q. Potential difference across each capacitor is same. So we put here Q equal to CV, then Q1 is equal to C1V, then Q2 is equal to C2V, then C3V. Take V common and cancel it with this V. You get C equal to C1 plus C2 plus C3. So, when 3 or more capacitors connected in parallel, the net capacitance would be sum of the individual capacitances. Suppose to select the values of C1, C2, C3. The values of C1, C2, C3 as 2, 3, 4. C is equal to C1 is 2 microfarad, C2 is 3 microfarad, and C3 is 4 microfarad. So it would be 4 plus 3 plus 2, that is 9 microfarad. So like this, we can work out numericals based on combination of capacitors. Fine. In exam they ask, in CBSE exam they ask, 2 capacitors of each capacitance C. C1 is equal to C2 is equal to C. There are 2 capacitors of each capacitance C. First they are connected in series, then they are connected in parallel. Then what is the ratio of their capacitances in series and parallel combination? First these 2 connected in series, CC. Then what is the net capacitance? 1 by CS. CS means the capacitance of 2 capacitors when connected in series is equal to 1 upon C plus 1 upon C. It will be 2 upon C. Therefore, CS is equal to C upon 2 for this equation. When the same capacitors connected in parallel, when they are connected in parallel, what is the net capacitance? CP. The capacitance in parallel combination is equal to C1 plus C2. C1 plus C2. Here 1 by C1 plus 1 by C2. Here C1 plus C2. So this will be equal to 2C because C1 is equal to C2. Call this is equation number 2. Then they have asked us to calculate what is the ratio of the capacitance from series to parallel. CS to CP. What is CS? CS is C by 2. What is CP? 2C. C cancels. So you get 1 by 4. So like this we can calculate numericals. Fine. Now let us go to the next topic. Energy stored in a capacitor. Energy stored in a capacitor. Look at the diagram here. One plate is connected to the positive terminal of the battery. Another plate of the capacitor is connected to negative terminal of the battery. This plate has acquired positive potential. This has acquired negative potential. And there is an empty space. The other day we learned that the capacitance of a parallel plate capacitor with a free space C is equal to epsilon naught A by D. Why? When this space is filled with some dielectric substance like mica, glass, then the new capacitance would be K times the previous capacitance. Fine. Now here is the topic. What is the energy stored in a capacitor? This battery keep on sending the charges to the capacitor. So, what is the amount of work done by battery in a given time? dW. dW is a small amount of work done in sending dq amount of charge from battery to the capacitor. So, work done is equal to potential into charge. Work done is equal to potential into charge. This potential is potential difference. V into the amount of charge, that is dq, sent from battery to the capacitor. But C is equal to Q upon V, or V is equal to Q upon C. Substitute this equation number 2 in equation number 1. We get dW is equal to P is Q upon C into dQ. If you take integration on both sides, dW is equal to integration on both sides, we get this one. We are charging this capacitor from initial charge 0 to final charge Q. Then what is the total work done? From initial charge 0 to total charge Q. This capacitor. What was the initial charge? 0. What is the final charge acquired by the capacitor? Q. Then integration of dW is W. W is equal to C is constant 1 upon C into Q dQ. Integration of, we learn integration of x raised to n dx is equal to x raised to n plus 1 by n plus 1. X raised to n plus 1 by n plus 1. Let us apply this formula here. Here, the value of n is 1. X is q. So, x raised to q raised to n plus 1. 1 plus 1, because the value of n is 1, divided by n plus 1. 1 plus 1. Limits from 0 to q. So, here W is equal to 1 upon C q square by 2, and substitute the limits from 0 to q. Now, all in work is equal to, you substitute the upper limit here in place of q, that will be q square. If you substitute 0 here, 0 by anything is 0. So what we get is 1 upon C in the bracket. First I will substitute the upper limit. I get q square by 2. Then I will substitute the lower limit. I get 0 by 2. I get 0 by 2. Here I have substituted the lower limit. Then W is equal to 0 by anything is 0. So q square by 2. Q square into 1 is q square. So I get q square by 2c. All that work done by this potential difference in sending the charge to the capacitor is converted into electrical energy and stored in the capacitor. So that energy is U is equal to 1 by 2 into Q square by C. Fine. This is one form of electrical energy stored in the capacitor. We can also write this equation two more forms. How do we write? U is equal to Q square by C. You substitute the value of Q is equal to CV. C is the capacitance of the capacitor and V is the potential difference. So if you substitute here in place of Q, what you get is C square V square by 2C. C square V square by 2C. Then C cancels. What you get is half of C square. This is second form of this equation. What type of energy is stored in the capacitor? Electrical energy. We also tell that the charges are stored in the capacitor. Fine. What is the other form of energy stored in the capacitor? In place of U, you can write UE also. UE. This way also we can write electrical energy stored in the capacitor. Whereas in inductor is simply a coil containing several number of turns. When electricity is passed through the inductor, the coil, then inside the inductor, in the inner part of the inductor, magnetic energy is stored. That magnetic energy, we will write that UV is equal to B square divided by 2 mu naught. Okay, this we will discuss little later. Okay, what is the other form of the energy stored in the capacitor? Substitute C is equal to Q by V here. So what you get is the energy, the electrical energy stored in the capacitor is half C is Q and this Q by V into V square. What you get is UE is equal to VV cancels half of